We now want to find the domain of a function algebraically, so we're not looking at the graph. We want to notice here that the kind of function we're looking at is a radical function, right? Because the x that is the independent variable is underneath the radical. That means there's some things that x cannot be, because remember, we want to keep the radicand to be a positive value, and the radicand is the quantity that is under the radical. If we have a radicand that's negative, the output y value would be imaginary, and that's not something that can be graphed. So the only x values that are allowed here are the ones that are going to keep this radicand positive. So what we'll do is we'll just grab up the radicand and say, who are the x values that make the radicand positive? So we'll just solve for x here. We'll set the radicand greater than or equal to 0. Solving for x is going to give us that x has to be greater than or equal to 4. We'll declare the domain in interval notation, and that is going to be starting at 4 and going off to positive infinity, which means that so long as the x value that I plug in is bigger than or equal to 4, we're going to have a radicand quantity that is positive and an output that is a real number, which is what's needed. And for part B, we're looking at another function, and what we'll notice with this function is that it's a polynomial. And when that's the case, then we get a free domain. When we notice that it's a polynomial, the domain is always all real numbers. And we can just copy paste the domain as soon as we realize that the function itself is a polynomial. Now we have a function that is rational. And with our rational functions, we want to watch out for 0 in the denominator. If we have 0 in the denominator, an x value that causes 0 in the denominator, we would have our output being undefined, and if the y-coordinate is undefined, that's not a graphable point, so we can't have that. So we need to figure out who are the x values that would cause this denominator to be 0. Well, in order to determine that, we would need to factor the denominator. This is a quadratic denominator that factors into x plus 3 times x plus 2, and from its factored state we can see more easily that if x is equal to -3, that would cause the denominator to be 0, so we'd have to leave that one out. And as well, if x is equal to -2, that would cause the denominator to be 0, so we also have to leave that out. Now, in order to determine what the domain would be then, let's think about these exclusions on a number line. -3 and -2 are to be left out, so those are not going to be included in the domain, but everything else is, and seeing it on the number line like this is going to help me to write the domain in interval notation. That's going to look like negative infinity is the smallest element in our domain, and we're going to go all the way up to -3 and leave that one out. In order to leave out just the -3, we have to then pick up with -3 on the other side. We have to start and stop with the same element in order to leave only one element out. Then we're going to go from -3 to -2, and we're going to leave that out, and in order to leave out just one element, we're going to have to stop and start with the -2 and then go on beyond -2 from there. This is the domain written in interval notation of the rational function up above. So here we have a function that kind of mixes it all up a little bit. We have x's under the radical, but we also have an x in the denominator of the fraction. So we've got basically two things that we're going to want to watch out for. The first is that we cannot have negatives under the radical, or we cannot have negative radicands. That's going to cause my output to be imaginary. We also cannot have 0 in the denominator because that would cause my output to be undefined. So let's just start with the first criteria. We know that we can't have a negative under the radical, and so what that means essentially is that the radicand, remember the radicand is the quantity that's under the radical, so in this case x minus 4, the radicand has to be a positive value if that radical is in the top of the fraction, it could be equal to 0. But our radicand is in the denominator of the fraction, and so if we had the square root of 0 in the denominator of the fraction, so whatever that x value would be up here, the output would also be undefined. So normally we would say that the radicand can be greater than or equal to 0, but if that radicand is in the denominator of the fraction, now 0 is no longer an option. So we can actually take care of both of these criteria by taking the radicand, making sure that it's positive, but removing the option for it to also be equal to 0. And our radicand in this case is x minus 4. So long as x minus 4 is greater than, strictly greater than 0, not equal to 0, then the x values are going to generate real outputs. So who are those x values? Every x value that is greater than 4 but not equal to 4. So check it out up here. As long as x is greater than 4, I'm going to get a positive radicand, and I'm not going to have 0 in the denominator. That is going to be our domain. So let's express our domain answer down here in interval notation. 4 is going to be the beginning of the domain. We're going to not include the 4, but have everything that is greater than that. So we'll start at 4 and go off to positive infinity, and this is going to be the domain of that function.